product moment correlation coefficient, or PMCC for short, is a measure of the strength of a relationship between two variables in statistics. It can help us quantify how strong or weak a positive or negative correlation is, if there is a correlation at all. These words you may be familiar with from the AS correlation and regression topics. As then with the A2 topics, we will also be coming to hypothesis test using PMCC as well, but that's for the second half of this video. To start off with, I'd just like to clarify that in most cases where you come across PMCC, you're going to be given the value straight up in the question. It's not going to be getting you to work out that specific value using the data from the actual scenario. That being said, just in case, and either way to give you some background context, that is where we're going to start. So, PMCC's formula is rather formulas within formulas. We're going to represent the value itself with the letter R, and we'll say that R equals the S of xy over the square root of sxx times syy, where in each case sxy is saying what is the average spread between the x-coordinate and y-coordinate of each point in the data. Sxx is the average spread between all of the x-coordinates, and syy is the spread between all of the y-coordinates in the data. In order to calculate these in turn, this is where we turn to those kind of sub-formulas, that which we have just on the right here. So to work out the S of xy, we'll be using the sum of xy, so this capital sigma here you should recognise from when we've done the standard deviation. So it's the sum of each x and y term times together. So the x and y of one coordinate times together, add the x and y of the next coordinate times together, and so forth. Then minus the sum of all the x terms times the sum of all the y terms divided by n, so the number of terms in total. And then similarly, just for your sxx and your syy, you'll then have the sum of x squared, so square all of the x terms first and then add them all up, then minus the sum of x then squared, so add up all the x terms first, then square the result, divided by n, and the same with the y's in each case. So plugging each of these sums into these formulas to get these kind of sub-answers, and then plugging those into the main equation for your PMCC, this has to get you an R value that is then between 1 and -1. The closer to 1 the value is, the stronger the positive correlation, the closer to -1, the stronger the negative correlation, and the closer to 0 in the middle, the weaker of either kind of correlation. So, for an example of this, we could have that for 10 instances of two variables a and b, the sum of a is 46, the sum of a squared is 270, the sum of b is 51, the sum of b squared is 339, and the sum of ab is 247. So find the PMCC, therefore, between a and b. So as we can see in this case, sometimes even if they are getting you to work out what the PMCC value is, they'll still give you a helping hand by telling you all of these sigma values straight away. So we can go into working out our S, or in this case SAB, SAA and SBB. For the first one, we're going to take that sum of, in this case, AB, so that's our 247, and we'll minus from it the sum of A times by the sum of b, so the 46 times by the 51, and then we know that there are 10 instances in total, 10 terms, so n is 10. Plugging all this into your calculator, you'll get an SAB of 12.4. For SAA, we're now going to have the sum of a squared, so your 270, minus from that the sum of a, so the 46, and then square that afterwards before, again, dividing by 10. Putting that in your calculator, you should get 58.4. And then lastly, for your SBB, we'll have the sum of b squared, which is your 339, minus from that the sum of b, which will just be your 51, square that, and again, one last time, divide by 10. This gets you 78.9. Now that we have these three values, we can switch to working out our R, our PMCC itself. So R is going to equal the 12.4 divided by the square root of 58.4 times 78.9. Okay, just putting that in the calculator all one last time, that gets you a product moment correlation coefficient of 0.1827 to 4 decimal places. This we would describe as a weak positive correlation. Obviously positive because it's a positive number, but it's weak because it's much closer to 0 than it is to 1. So there is something of an upward trend if you were to plot it on a scatter graph going from bottom left to top right, but the point's nowhere near close enough to really be called a straight line. Okay, so if we can see how we've been able to use these sigma terms to work out our respective S terms, which will then get us the ultimate PMCC, and how we can then comment on that PMCC, let's just see how you could get along with the first example of your own. Now, this will be one of those instances where the question will be completely unhelpful to you and only have given you the actual raw data. They haven't even worked out the sigma terms, let alone the R value. So you're going to have to work it all out from scratch for yourself. So think about how you're going to get like the sum of P, the sum of Q, the sum of PQ, and so forth. And then again, follow the steps that have been done on the left here. Once you have that, find your PMCC and comment on what correlation there is, therefore, between P and Q. Pause the video, have a go for yourself, and then press play again when you're ready to compare. So, to start off with, because we can work out these sigma values really in any order, I'm actually going to start by working out what each of the PQ values are going to be. So 6 times 2 is going to get you 12, then just going down for each of the rows, you should have 24, 9, 24, 14, and 9. Okay. Now from this we can start adding them up, so the sum of just P on its own, so the 6 add 4, add 3, add 3, add 2, add 1, that should get you 19. The sum of P squared, so each of those squared, so 6 squared, add 4 squared, add so forth, 36, add 16, etc, etc, that should get you 75. So then do the same with the Q's, so the sum of Q just in general, so 2 add 6, add 3, and so forth, that should be 35. The sum of Q squared, so 4 add 36, add 9, that's going to be 243, and then the sum of those PQ values here, so 12 add 24, add 9, so forth, that gets you 92. So to now plug these into your S formulas, so for the S of PQ, we're going to have the sum of PQ, that 92, and minus from that the sum of P, which was 19, times by the sum of Q, which was the 35. Divide that by, there are 1, 2, 3, 4, 5, 6 terms. So that gets you a value here of minus 18.83 recurring. As for SPP, that's now going to be your sum of P squared, so 75, minus the sum of P, 19, afterwards squared, again divided by 6. That should get you 14.83 recurring again in terms of the decimal. Then SQQ, that's going to be your sum of Q squared, the 243, minus from that the sum of Q, the 35 squared, divided by 6, and that gets you 38.83 recurring. Finally then, just to put these into your PMCC formula, you would have that R equals the minus 18.83 recurring over the square root of 14.83 recurring times the 38.83 recurring, and this would get you a PMCC of, to 4 decimal places, minus 0.78 0.47. What can we then say about this correlation? Well, it's a strong negative correlation. Negative obviously because there's a minus sign, and it's strong because it's closer to -1 than it is to 0. Okay? Well, if we're happy with that, let's move on to perhaps what you're more often going to come across, which is the hypothesis testing of your PMCC. Now, there's actually two ways we can go about this, two styles of question. To address the first one, we could have that when investigating whether there is a correlation between height and weight, a sample of 23 people had a PMCC of 0.5711. Test at a 1% significance level whether there is a positive correlation. Now, some of this phrasing should sound familiar to you, as well it should from binomial hypothesis testing. It is a similar concept after all. For instance, the word significance level should be ringing some bells. Well, as per when we do binomial hypothesis testing, we're going to need some hypotheses. A null hypothesis and an alternate hypothesis. The former being what we currently take to be true, and the alternate being what we're testing for, this new idea which might actually be the case. In these, when we're looking at the correlation that we're testing for, the symbol you may see used is the Greek letter rho, which is like a slanted P, just as how we use the Greek letters pi and sigma and others in other places. The null hypothesis for a correlation hypothesis test is always that rho equals 0. That is never going to change. But then here, the alternate is what depends on the statement. In this case, because we're looking for a positive correlation, we're seeing is rho greater than 0. Now that we have this, we need our other parameters. Before, we would have had like n and so forth for a number of trials. Here, specifically, you may see that written instead as your sample level. That is, again, though, still just how many terms are there. In this case, that's 23. Then we also need to identify our significance as a decimal. In this case, 1% is just going to be 0.01. And we leave it as is because this is a one-tailed test. If you want to go over the difference between a one and a two-tailed test, you can go back over that when we do our binomial hypothesis testing. Now, to perform the test itself, you may very well have a function in your calculator where you can just plug these figures in and it'll work it out for you. The critical value which you can then use to check for your alternate hypothesis. However, if you do have to do this a bit more old school and use the contents of the formula booklet, then you will turn to the table that's labelled critical values for correlation coefficients, find the part of it that's talking about PMCC, and then you'll need to cross-reference in the columns and rows, find the number that is under / next to both the significance level of 0.01 and the sample level of 23. In this case, the number that you should be able to find on the table or that is spat out by your calculator should be 0.481. This critical value is what we're now going to compare to the PMCC given to us in the description, that being the 0.5711. How do we compare though, and what does it mean? Well, the rules for the critical value here are very similar to the rules that we use in binomial hypothesis testing. So we can either have that the critical value is less than, and rather than the significance level in this case, here we're comparing with the modulus of the PMCC that the description gives us. If you're not familiar with the modulus from Pure yet, this is just something that basically tells you to ignore the minus sign. So if you had a negative PMCC given to you in the question, just forget the minus, look at it just as the magnitude of the value, the decimal itself. So if this critical value is less than the modulus of R, then you take H1. You say that there is enough evidence, in this case, of a correlation. However, if the critical value had been greater than the modulus of R, then you keep the null hypothesis. There is not currently enough evidence of a correlation. in this case, 0.4815 is indeed less than 0.5711. Therefore, we'll say there is enough evidence to take the alternate hypothesis. There is indeed a positive correlation between height and weight. Now, the other form of hypothesis testing for PMCC, which is actually, at least in my experience, rarer but still possible, works on some similar principles, but obviously is different in others, otherwise there wouldn't be this distinction. If we just read through the question again first, and then just get into the semantics of it, the PMCC between daily mean temperature and daily mean pressure is minus 0.1491, with a p-value of 0.06. Use a 2.5% significance level to see if there is evidence of a negative correlation. Well, in this case, again we've been given a significance level, and again we've been given a PMCC. But we don't have a sample size, we don't have an N, so we can't use the same method as before. Instead, we have what's called a p-value. Now, in essence, what this p-value is doing is giving us a means of judging, is this PMCC value likely to fall within some critical region? That is to say, is this number here going to be enough to get us to take the alternate hypothesis? Well, for that, therefore, we need our hypotheses once again, and once again they're basically going to be the same as before. The null hypothesis has to be that rho equals 0. And for the alternative hypothesis, this time, because we're checking for a negative correlation, it'll be that rho is less than 0. Now, we are about to go back to comparing to the significance level, as we did with our binomial. So in the above example, you're taking the critical value side of things. In the second example, we're taking the significance level side of things. If your p-value is less than the significance level, you will take your alternate hypothesis because there is enough evidence. If, however, your p is greater than your significance level, then you will keep your null hypothesis because there's not enough evidence. So, if you have this p-value instead, all you need to do is just compare it to your significance level and just say, okay, our 0.06 for our p-value, how does that compare to the significance level as a decimal, which would be 0.025? Well, in this case, the p-value is greater, therefore this fits the second criteria, therefore there's not enough evidence. We keep our null hypothesis. If we can just acknowledge the distinction between these styles of wording of question, therefore, and how we can just go about basically the same hypothesis test, just using slightly different figures in slightly different ways, let's just see if you can have a go at some other examples of your own. So on the right, first of all, we have that when investigating test marks and social media usage, a sample of 13 shows that R equals minus 0.6101. Test at a 2% significance whether there is any correlation. And then the PMCC between travel time and fuel cost is 0.3649 with a p-value of 0.006. Use a 4% significance level to see if there's evidence of a positive correlation. So, consider how the wordings of these questions are the same as the ones on the left, how also they are different and what implications those differences might have on your method of working. Maybe again think back to what we've done with binomial hypothesis testing if you're unsure. But either way, just pause the video, have a go for yourself, and then press play again when you're ready to compare. So, if we were to look at the top one first, because it's a hypothesis test, we need to acknowledge what our hypotheses are. Once again, null hypothesis has to just be that rho equals 0. But in this case, for our alternate, there's no mention of a positive or a negative correlation. We're just testing for any correlation full stop. Therefore, that's to say that rho simply doesn't equal 0. Now, what this is telling us is that this is going to be a two-tailed test. And the significance of a two-tail is that we have to split the significance level in half. So here, even though the total significance is 2%, we're going to be testing against 1%. Now, unlike when we've done our binomial and so forth, there is no way of doing, okay, we'll look at greater than or less than. You've only got a single value that you can read off of your table or get out of your calculator, so that's not going to make a difference in this case. We're still just going to look at a sample level of 13 and a significance of that 1%, which as a decimal is going to be the 0.01. Now, unlike when we did the binomial hypothesis testing where we had a two-tailed test, there's no way of distinguishing between doing the greater than and the less than to do both sides of the inequality this time. There's only one value that you can get out of the table or from your calculator for this sample level and significance level. So that means we simply have that single critical value of 0.6339. So it's simply this that we will compare to the modulus of the PMCC that the question gave us, which was our minus 0.6101. Now this modulus is just making us ignore that minus sign here. So just to compare these two, while they are close in magnitude, the critical value is just bigger. Well, what do we do if the critical value is bigger than the modulus of the PMCC? Well, that means that there's not enough evidence, that for now we have to keep with our null hypothesis. As for that other question, once again, for a final time, we'll establish our hypotheses. So, as ever, null hypothesis, rho is 0. But here, for the alternate hypothesis, we're back to having an inequality because the question is specifying a positive correlation. So here, we'll be looking at rho being greater than 0. For this question, though, because it's a p-value question, we then only have to compare this number here, the 0.006, to the significance level, and because it's a one-tailed test, we're back to just inequality. We don't have to change that. It could just be written as 0.04 as a decimal. Which is bigger? Well, that's the significance level. What do we do if the p-value is less than the significance level? That's when we say there is enough evidence and that we do therefore take our alternate hypothesis, in this case saying there is enough evidence that there is a positive link between travel time and fuel cost.